Good morning to everyone. Myself, I am G. Charan from Triple E branch. Today's my tech talk topic of analog electronics is the successive approximate register ADC parasitic building blocks for ultra power to ultra high speed applications. A successive approximation of ADC is a type of analog to digital converter that converts a continuous analog waveform into a discrete digital representation using a binary search through all possible quantization levels before finally converging upon a digital output for each conversion. One of the most common analog to digital converters used in application required a sampling rate under 10 MSPS is the successive approximation register. This ADC is ideal for applications requiring a resolution between 8 to 16 bits. The successive approximation register ADC is a must known, one of the most common analog to digital converters used in application requiring a sampling rate under 10 MSPS is the successive approximation register ADC. This ADC is ideal for application requiring a resolution between 8 to 16 bits. For more information or resolution and sampling rates, please refer to the first in this series of articles. Disappearing resolutions and sampling rate, the ADC is one of the most intuitive analog to digital converter to understand, and once we know how this type of ADC works, it becomes apparent where its strength and weakness lie. Basic operations of the SAR ADC, the basic successive approximation register analog to digital converter is shown in the schematic below. Basic successive approximation register analog to digital converter. The SAR ADC does the following things for each sample. The analog signal is sampled and held. For each bit for each bit, the SAR logic outputs a binary code to DAC that is depends on the current bit under scrutiny and the previous bits already approximated. The comparator is used to determine the state of the current bit. Once all bits have been approximated, the digital approximation is output at the end of conversion. EDC full form is end of the conversion. If we consider the example of an analog input value of 0.425 value and a voltage reference of 1 voltage, we can approximate the output of an 8-bit ADC as follows. Set first bit of 8-bit output to 1. So output to DAC is 0.5. 0.5 subtracted from 0.425 is less than 0. So set the first bit of output to 0. Set second bit of 8-bit output to 1. So output to DAC is 0.25. 0.25 subtracted from 0.425 is greater than 0. So second bit of output is 1. Set third bit of 8-bit output to 1. So output of DAC is 0.375. 0.375 subtracted from 0.425 is greater than 0. So third bit of output is 1. This process is repeated for all 8 bits until the output is determined to be 0, 1, 1, 0, 1, 1, 0, 0. It becomes apparent from this process that an n-bit SAR ADC must require n clock periods to successfully approximate the output. As a result of this, all through these ADs are low power and require very little space. They are not suitable for high speed, high resolution applications because these ADCs require very little space. They are often found as a peripheral inside microcontroller or in an extremely small package of clock period. Perhaps slightly less intuitive is the fact that power deception scales with the sampling rate. As a result of this, these ADCs are ideal for use in low power applications where the ADC is required to take samples infrequently. One thing is to note in this architecture is the lack of pipeline and the latency associated with this as a result. This SAR ADC is suitable to multiplexed applications. The two features of ADC that define the overall characters of the ADC are not surprisingly the DAC and the comparator. Successive approximation analog to digital converter circuits typically consists of four chuff sub-circuits. A sample and hold circuit to acquire the input voltage win. An analog voltage comparator that compares win to the output of the internal DAC and outputs the results of the comparison to the successive approximation register. SAR full form is Successive Approximation Register. Successive Approximation Register. Subcircuit designed to supply an approximate digital code of win to internal DAC. An internal reference DAC that form comparison with VREF supplies the comparator with an analog voltage equal to digital code output of the successive approximation register. The successive the successive approximation register is initialized so that the most significant bit MSD is equal to a digital one. This code is fed into the digital analog circuit which then supplies the analog equivalent of the digital code into the comparator circuit for comparison with the sample input voltage. If this analog voltage exceeds when the comparator causes the SAR to reset this bit, otherwise the bit is left as 1. Then the next bit is set to 1 and the sample test is done by continuing this binary searching until every bit in this successive approximate register has been tested. The resulting code in the digital approximation of the sampled input voltage and is finally output by the successive approximation register at the end of conversation. One of the most common implementations of the successive one of the most common implementations of the successive approximation ADC. The charge redistribution successive approximation ADC uses a charge scaling DAC. The charge scaling DAC symbol consists of an array of individually switched binary weighted capacitors. The amount of charge upon each capacitor in the array is used to perform the aforementioned binary search in conjunction with a commutator internal to the DAC and the successive approximation register. This intensity integration of system on chip and the growth of portable application market derives the research of solution alternative to standard circuit design that can capable to further reduce the power consumption of the entire electronic system. Next to general low power circuits, there is an emerging product applications area characterized by even stronger power requirements, the so called ultra lower power electronic. Radio frequency identification RFID. Radio frequency identification use electromagnetic fields to automatically identify and track tags attached to objects. An radio frequency identification system consists of a tiny radio transponder, a radio receiver, and transmitter. When triggered by an electromagnetic interrogation pulse from a nearby RFID reader device, the tag transmits digital data, usually an identifying inventor number, back to the reader. This number can be used to track inventor goods. Passive tags are powered by energy from the reader's interrogating radio waves. Active tags are powered by a battery and thus can be read at a greater range from radio frequency identification reader up to hundreds of meters. Unlike a barcode, the tag does not need to be within the line of sight of the reader, so it may be embedded in the attracted object. Is one method of automatic identification data capture. AIDC full form is automatic identification and data capture. Among different ADC architecture, the successive approximation register ADC has flexibly architect high power efficiency and is suitable to the digital CMS process. A time intervals or a generator has been implemented in different technologies. Simplest of with a memory block sorting the digital result from ADC. Thank you.